Hey guys, this is our hurricane video makeup lecture on section 6.5, which is average value and not arc length. My apologies if you guys caught the wrong section on accident. Couple comments that I wanted to start up before this video got going. One, again, my apologies if you caught that other video. We will need to go over arc length at some point, but not until test 2, so you guys are a little bit ahead in that regard. Comment number 2 that I wanted to make. You may have noticed, if you're paying attention to the section numbers, that we're doing this a little bit out of order. 6.5, which actually is average value, I promise. This does not immediately follow the section that we left off with when I last saw you guys on campus. That's okay. We don't need 6.3 or 6.4 for this section. I'm just trying to cherry pick some of the easier stuff for you guys to do with video lectures so we can do the harder stuff together on campus. Comment number 3. If you're a person that really doesn't like videos, I'm planning on pulling the PDF of these notes and posting it on Moodle with the rest of the lecture notes so you can read them rather than watch the video if you would like. Comment number 4, if you watch the video or if you read the notes, either way, keep an eye out for the quiz that's going to be on that last page. Okay, so that's going to show up either way. Without further ado, I'll go ahead and get started. 6.5, average value. Rather than starting out with definitions or theorems or anything, I'm going to give you guys a motivating problem for this section. We're out for weather-related events, so go ahead and make this a weather-related motivating problem. How do I compute something like average temperature for a given time period? Now, I could have picked something different. Who knows? Like, how do I compute like average pressure? Or how do I compute my average, whatever, who cares? I picked this one because it's probably something you've run into before, so you hopefully have at least an idea of what you want it to mean. You want this to be a useful number. Like if you're looking up average temperature for a given day that is projected, maybe you want to know like what to wear or what to pack somewhere. Or maybe if you're looking at a larger time period and maybe thinking about things like global warming or climate change, you want this number to mean something. How do we compute this so it actually is a meaningful quantity that's maybe not biased towards certain things, right? How do I compute this? Now, part of the reason why I pose this as an interesting question is that usually when we say the word average, it's interpreted as statistical mean. And what I mean by that is, I'm sure you guys have computed this before, you average n numbers by adding them all up and then dividing by n. So for example, if I wanted to average 5 numbers together, I would add them all up and then divide by 5. Now, this poses a potential problem for us if we try to interpret average in that manner because, this is the way that we usually think of temperature graphs, this thing that I've drawn here, where I have time on the independent axis and temperature on the dependent axis. Haven't given units, but they're not super important for us for our purposes. This is not a discrete list of data points, right? This is a continuous graph. I plug in a time, I get a temperature back. It's not like I've got a list of temperatures that I can add up together and then divide by n. What is n here, right? So how might I find average temperature if this is my situation, right? How do I reconcile this problem? Well, some of you guys might have had a couple ideas on how to do this while I've been speaking. Namely, pick some times. Treat the average like normal. Now I'm going to ignore this phrase for the moment. We'll talk about why I included that later on. But it's not a bad idea, right? Pick a handful of times. Let's say I pick something here like T1, T2, and T3. pick my times. I only did 3 because I don't want to clutter up my diagram, but look at the temperatures that happen at these times. I'll use capital letters to denote these: T1, T2, and T3 here. Okay, and once I have those times, I can actually average these guys together. So, like I said before, the way that we run an average would be add up all the numbers that are of interest and then divide by however many numbers we had. And that would serve as our approximate average temperature here. Now, there are a couple, potential issues or points of concern here, like, why did I pick 3 times? What could I have done to maybe, like, get a better average? Is there a canonical or, good to pick number of times that I want to split things apart into? Well, here's where I want to tie this into calculus, right? For me to get a really good idea of how I might calculate a super meaningful average temperature. I really want to tie this into integrals, and a good segue into that is trying to tie this into Riemann sums. Now, my sneaky way of doing this is this assumption that I'm making each of these things a unit apart. Now, here's the reason I did that. If I assume that each of these little subintervals that I picked are evenly spaced, I wasn't just doing that, to clean up my diagram. If I make each of these guys about a unit wide, that means that the entire, interval that I'm choosing to investigate this average on is 3 units wide. And that happens to be what we are dividing by for this average. So I'm trying to find a way to tie in the length of this interval along with, the way that I naturally would compute my average. Now, if I had picked a different number of times per this scheme that I've set up, say I'd picked 5 times, and I assumed that each of them were a unit apart, well, I would have 5 of these intervals, and 5 copies of one would have given me, a 5 to divide by instead. So one thing that we could notice, if I want to make this association between what we're doing with the average and what we're doing with Riemann sums in Calculus 1, well, what we did above has the same exact effect as taking a Riemann sum to approximate the area underneath this curve, and then we ended up dividing by the length of the base, like I discussed before. Now, if you didn't see it, I'm going to go ahead and make it super obvious here. Here is my time 1, my time 2, and my time 3. So I'll go ahead and label these again. And once I plugged time 1 in, I got some sort of height capital T1. If I plugged time 2 in, I got some sort of height capital T2. And if I plugged T3 in, I got some sort of height capital T3. Now, remember, when I said that everything was going to be 1 unit wide, that actually makes computing the areas of these rectangles really, really easy, because base times height is just 1 times whatever the height is. That meant that this first guy is 1 times T1, so that has an area of T1. This is going to be 1 times T2, so this has an area of T2, and this last guy similarly is going to have an area of T3. So, if I'm taking a Riemann sum, that's adding up all of those areas of rectangles, so I'll get T1 plus T2 plus T3, and if I'm dividing by my length of my base, well, my length of my base is just going to be 3. It's the same thing that we did above, except for now I'm interpreting it in terms of calculus. Now, part of the reason that I want to interpret this in terms of calculus is I want to know how to make my number better, right? This is just an approximation. There wasn't even any good reason that I picked 3 data points to work with, aside from the fact that it would be easy to draw. And that doesn't really speak too well for it actually being a good number to choose for getting a reasonable value back at the end. How can I improve on this method? Well, there are a couple things that you can do. For Riemann sums, we always said that those get better if you take more sample points, and my average temperature approximation is going to get better with more sample points too. Reason being this. I'll give you guys an example. If I tried the same trick for this different temperature diagram that I did for my last one, well, the T1 and the T2 and the T3 from last time, these coincidentally are really sucky representations of what's happening with my temperature in this particular situation. You notice that these just happen to fall on my outliers, places where my temperature spikes. If I picked each of those values, I would probably get an average that was like way up here, and that's really not indicative of my general situation, which seems to have a baseline kind of closer to down here. So, to demonstrate, the more sample points you pick, the better your average gets. If I started to pick more data points than just T1, T2, and T3, let's say I picked one in the middle of each of these intervals, or heck, let's say that I added in even more and went in with the midpoints of those. If I have temperatures corresponding to every single one of these data points, you'll notice that I'm more likely to hit each of these places where my temperature is lower and more reflective of my general situation. So now I've got like 9 data points that are at the lower temperature and only 3 that are at my outliers instead of all of them at my outliers. And that's probably going to pull the average back down to something that's a little bit more reasonable in this situation. Okay, so more data points, better temperature average. And actually, what this is really suggestive of is taking a limit, right? We said that more data points and more data points and more data points means a better, quality answer, but I don't want to sit here and be number crunching like hundreds and hundreds and hundreds of data points. It's probably going to be easier if I just get an integral going here, right? Because that's what the Riemann sum turns into in the limit, is the definite integral. So what this is really suggestive of, okay, if we said before we were taking the Riemann sum and dividing by the length of the interval, this suggests that it would be a lot smarter if we just took the definite integral instead and divided by the length of the interval. Now, we don't necessarily have to care about temperature when we're doing this. We could just use this for general functions because, temperature isn't the only thing that we measure that maybe we're interested in finding averages of. Maybe you want average pH or average power output or average, who knows, right? We can still use this idea where we take an integral of our function that we want an average of, and then we divide by the interval length of input values, and that'll give us averages of our output. Okay, now if all the justification stuff went way over your head and you would like a formula to sort of explain what's going on here, this is actually the formula that we really want to be looking at, right? Average value of a function on an interval is given by what we just said. You are going to take the definite integral of the function that you are looking at and you divide it by the length of the interval. This is what b minus a is. Tells you how long that interval AB is. So your textbook and your web assignments are frequently going to denote this quantity as f_av. We use this notation when it's pretty clear what function we're dealing with and what interval we're dealing with, and in general you're going to be given both whenever you want to compute average value. Okay, so I'll go ahead and try to do some rudimentary examples here so you guys can get a feel for how the formula works. Let's see if we can go ahead and do this. Try to pick a pretty straightforward example for y'all. Let's try average value for f of x equals x on the interval from 4 to 10. First thing I'm going to do is start out with my formula. Okay, I'm not doing anything fancy yet, except for just copying down what's going on with my formula that I just showed you guys on the last slide page. Okay, this is pretty straightforward. It's very plug and chug. The main parts where this is going to potentially be hard is if you guys have like a hefty function to integrate here, but I'm trying to start us off easy. Interval goes in for b and a, and your function goes in for f of x, right? The interval was from 4 to 10, so this is going to be 1 over 10 minus 4, just to get the length of the interval. The interval was 4 to 10, so that is also what we are integrating on, and I just told you guys the function was x, so that's what we're antideriving. All I got to do is just simplify this, right? So if I clean this up, both my fraction and the antiderivative that I actually need to take here, which gives me x squared over 2. After I antiderive, I need to evaluate on the bounds. I will simplify this a little bit before I do that so I have less clutter going on. But once I evaluate this thing on the bounds, I'll scroll down so I have room. I'm just plugging in the top number, and then I'm subtracting what happens when I plug in the bottom number. Now if I do that in this particular case, this actually simplifies down in a very nice way. I get a round number even, because 84 divided by 12 is 7. What this tells me is that my average value for my function on that given interval comes out to 7. Now, if I actually want to look at the function that I was using again, f of x equals x, on the interval 410, here's kind of what that's saying, and it's a nice way to get a geometrical interpretation of this. I've got this function, y equals x, on the interval from 4 to 10. So that's going to be, this region right here. What I did was I found the area of this bit, and then I divided that by the length of the base. Now, if you're thinking about what that means in kind of area terms, I've got this area that I'm dividing by a length. Naturally, we might want to interpret this as kind of like another length. Well, the way that we do this is as follows. You may notice that if I plug in these endpoints, this comes out to 4, this guy comes out to 10. My average value happened, just luckily, to be smack in the middle here, right? Okay, right at 7. Here's why. You kind of want to think about geometrically what's going on is kind of like this. If I viewed this region that I've shaded, okay, if I viewed this guy as something that I could kind of mush around and reform and like repack into a different shape, what would happen, right, if I mushed that area around? Well, if I give you guys a container, okay, that's only as wide as the interval that we're working on, but I allow this region to kind of be mushed around and played with, you'll notice that this region up here that's above this dashed line is about the same size as this region over here. It's maybe not super clear because, hand-drawn drawing, but if I were basically to repack this shaded region, I could repack it into a rectangle. And specifically, I could repack this shaded region right here. I could repack it into a rectangle that was 7 units tall, right? So this is a nice geometrical interpretation of my average value. If you could kind of squish your area down so it was all of even height, of an average height all the way across the region, that's where this average value is coming into, okay? And the reason that this is so nice and symmetric, okay, 7 falls immediately between 4 and 10, and in fact 7 is the average of 4 and 10. This is just because our function is really nice and pretty and symmetric, right? This isn't curved in any weird way. It's not super skewed towards 10 for most of the interval. It's pretty evenly spaced. So pretty easy to picture what's going on when we mush our area around here. Another kind of example that I could play around with if I wanted to give you guys some sort of, maybe one that we could guess if we thought about it really hard. If I find the average value of cosine in the interval from 0 to 2 pi, again, I will start out with my formula for f av. This is 1 over b minus a times the definite integral from a to b of f of x with respect to x. This is very plug and chug. I just need to stick in my endpoints of my interval into my formula along with the function that I'm given. Now, this isn't a particularly bad integral. I've given you one that's a basic rule, and antiderives to sine of x. I've given you nice values that are on the unit circle, which, if I go to evaluate between the endpoints, I'm getting 1 over 2 pi sine of 2 pi minus 1 over 2 pi sine of 0. Now, 0 and 2 pi actually correspond to the same angle on the unit circle, so both of those are going to come to the same value, but even if they didn't, sine of both of those angles is 0. So this is going to come out to 0 minus 0. I'm getting 0 back as my average value. Again, if I wanted to kind of geometrically interpret what was happening in this particular situation, you may note that on the interval from 0 to 2 pi, this coincides precisely with one period of the cosine function, right? Because we come down here, we dip up, and then we come back here. This function spends pretty much about as much time above the x-axis as it does below the x-axis because it's, symmetric in that manner. So again, if we were thinking about fixing, the interval that we worked on and thinking about, mushing around some of these areas, okay, including the fact that some of our areas count as positive and some of them count as negative, if I mush these around on this interval, they all balance each other out. So, average value for this guy ends up being 0. Spends just as much time above the axis as it does below. Now, let me do one that's maybe a little bit less geometrically inspired, just to show you guys kind of how tricky some of these can get. Main thing that's going to make these tricky is going to be the type of function that you're facing. So if I go to lay out my formula here, well, oops, let me get my fraction in first. Pretty much my setup is still really, really basic. I just get to plug and chug, right? So my interval goes in where it needs to go in, and my function goes in where it needs to go in. Well, not much is going on with this fraction out front. That simplifies to 1, so my main focus is really going to be on integrating this function I've given you, and y'all should hopefully recognize by now that sometimes the functions I give you are kind of tricky, right? A case like this, I see that there's composition. It's probably a good sign that I want to try something like U substitution. If I try that, good U is typically going to be on the inside of a composition, so x squared plus 1, probably a solid choice for U here. If I do U substitution, my next step is to find a du. We do that by deriving and slapping a dx on the end. I need a way to plug this back into my integral, but there's not a leftover 2 in my integral. There's just the leftover x and dx. So I'm going to have to correct my constant coefficient here. I can do that by dividing both sides of that equation by 2. So now I'm ready to plug everything back in. I'm going to scroll down to give myself a little bit of room here. If I go to clean this integral up, I am going to get that I no longer have e to the x squared plus 1. It is really e to the u. And I no longer have x dx. We have decided this is really a half du. Now, I could try to antiderive this and then plug x stuff back in and evaluate then, but I prefer to change my bounds over. The way that we do this is you basically want to take these bounds, stuff them into your u function, and then that'll give you new bounds. So if I plug in 0 to u, this is 0 squared plus 1, I get 1. If I plug in 1 to u, it's 1 squared plus 1, I get 2. These are my new bounds. And at this point, I never have to go back to x. I can just directly evaluate my integral here. So I'm going to go ahead and get a half e squared minus a half e to the 1, but really that's just e. Okay, so this guy, even though it's kind of messy, this is going to be the average value of that function on that interval. I'm going to try one more example here to show you guys kind of a tricky case. Let me see if I can make this a little bit more legible here. Let's see if we can find the interval from 1 to b. Okay, this is meant to be a b. This is not me having a crappy 6 up here, but find the interval from 1 to b on which the average value of that function is equal to 6. This is why this one's weird, okay? Usually I start these guys out by giving you guys the formula, or rather, remembering or recalling the formula, which looks like this guy. And then we plug and chug and we find the average value. Now you'll notice what's been given to you in this problem is a little bit different. There's actually a couple on WebAssign that might be like this too. Instead of being given the full-on interval and the function, you guys are being given part of the interval along with the function, and y'all are given the average value. That's the thing we've been computing the last couple times. So instead, before there was one unknown, we were given both parts of the interval and the function, but the average value was missing. That means we're solving for something different this time. Okay, so if I plug in all the stuff that's known, we know a, so that's going to give us this guy and this guy. We know my function, that's going to give us this guy. And we know my average value. That's actually going to give us this guy. So what this is suggesting is we want to set this up like an equation, okay, and then actually solve for the missing part. Now, I can go ahead and plug in everything I know. We said the average value was 6. I will try to hook these a little bit to make it a little bit more obvious where my 6's are and where my b's are. Average value is 6. We do not know what b is. We do know what a is. Okay, and again, to reiterate, we know a, but we do not know b. And my function is 2x minus 1. Now at this point, my b's are all mixed together and jumbled in integrals and stuff. I really want to simplify this to work on it, so I am going to try to take that integral, right? I have a 1 over b minus 1 that I'm going to hang on to. Don't know what to do with that yet, but we'll wait. And I need to antiderive this. Well, the antiderivative is a polynomial in this case. I tried to not overwhelm y'all with different hard parts of this problem, so at least the antiderivative wasn't bad. And now, if I want to keep simplifying, I need to start plugging stuff in. Alright, so if I start plugging stuff in, I'm going to get, to plug in b first, this is b squared minus b, and I subtract off what happens when I plug in 1. Well, if I plug in 1, this is 1 squared minus 1. Hopefully we recognize that that drops off. Okay, that simplifies to 0. Now there are a couple different ways you could go. You could try to, multiply both sides by b and, move stuff to one side and factor and whatnot. But if I'm really careful and observant here, you guys may note that, well, this is a thing. If I factor out this expression, I'm getting b times b minus 1, these terms actually cancel, right? So the thing that I suggested before, if we multiply both sides by b minus 1, well, there's a b minus 1 on both sides. You may as well divide it out. So this isn't really going to give us any helpful information. I'm going to just let those cancel, and then that's going to give us that 6 is b here. Okay? So if I come back to the original problem statement, find the interval on which the average value is yada yada. This is going to tell me that my interval goes from 1 to 6. Okay? So a little bit different of a problem, but again, pretty plug and chug. Now, some comments I'll leave you guys on. Again, in general, the main thing that makes these tricky is integration, unless you run into one of that last kind of problem. So do make sure that you know your rules, you know your simplification tricks, you know how to do U-sub. I'll kind of give you guys a little bit of a test here and throwing a quiz problem at you. This is the one I warned you about. Just give me the average value of that function on that interval. If you have questions on this, you're welcome to let me know. If you need to turn this in late, if you're not ready to immediately hand it in when we get back, that's fine. Come ask me about stuff. Turn it in when you feel comfortable, okay? And in general, if you guys have questions, you are welcome to email me while we're out. If you have issues turning stuff in, if you're running into problems due to the hurricane or travel related to it or anything, I am going to try to be really flexible, okay, while we're out, because I know that crap happens, right? So whenever you are capable of having power back, internet access, whatever, actually being in a good spot to worry about your work, feel free to let me know if you're running into problems, or if you are in a comfortable spot to get your work done, do feel free to ask me questions as well. Okay? Till next time, guys.